In this example, a rod of length 12 centimeters is heated at one end of the rod. We are given selected values of a function t of x, which represents the temperature in degrees Celsius of the rod, and x is measured in centimeters from the heated end of the rod on the closed interval from 0 to 12 centimeters. In part A, we want to use the value in the table to estimate t prime of 8, which represents the derivative of the function t of x when x is equal to 8. We know that whenever we are given a table of values and asked to estimate the derivative, we are going to use the average rate of change formula over an appropriate subinterval which contains the value of x where we are trying to estimate the derivative. In this case, we are going to estimate the derivative when x is equal to 8, and looking at the selected values of t of x, we clearly see that x equals 8 falls in between x equals 7 and x equals 9. Therefore, I set up my difference quotient for my average rate of change as t of 9 minus t of 7 divided by 9 minus 7. Looking to the table of values for t of 9, I see that I get 54 as that value, and t of 7 is going to be 60 divided by 9 minus 7, which is 2. A quick calculation tells me that the estimation for t prime of 8 is negative 3. But before I move on, I want to think about the units. This was a difference quotient, and in the numerator, I subtracted two t of x values, which were both measured in degrees Celsius. Therefore, the unit of my numerator is degrees Celsius. And in the denominator, I subtracted two distances which were measured in centimeters, and therefore the unit of my denominator is centimeters for an overall unit of degrees Celsius per centimeter. In part B, we want to use correct units to explain the meaning of t prime of 8 in the context of the problem. And so pulling over our answer from part A, we found that t prime of 8 was approximately negative 3. We know that in the context of real-world applications, the derivative represents the instantaneous rate of change of the function. And so in this case, t of x represents the distance, the temperature of the rod x centimeters from the heated end of the rod. And so therefore the derivative of t of x, which is given by t prime of x, will be the rate of change in the temperature in degrees Celsius per centimeter of the rod. And so here is my answer. I say when x is equal to 8 centimeters, the temperature of the rod is decreasing at a rate of 3 degrees Celsius per centimeter. The reason I knew that the rate of change was the temperature was going to be decreasing is because the value of my answer was negative. So I want to point out a couple of things about my answer. The first is that my answer has a noun in it. I use the temperature of the rod as the noun of my sentence because that is what the original function t of x represented, and I used that language directly from the problem. As you can see back up in the header of the question, it tells me that t of x represents the temperature of the rod. The next thing that my sentence has is it has a reference to the independent variable, which in this case is x, which represents the distance from the heated end of the rod. And so I have that at the beginning of my sentence. You could also have that at the end of your sentence if you would rather put it at the end. The last thing that is needed in my sentence is a discussion of units. And so you can see that I have units on both the dependent variable at the end, degrees Celsius per centimeter, and the independent variable, the x is equal to 8 centimeters. In part C, we are asked to explain why there must be a distance on the open interval from 0 to 12 such that the temperature of the rod is 63 degrees Celsius. The first thing that I notice is that the beginning of this question indicates to me that I am going to use one of the existence theorems that we are going to learn in calculus. In calculus, we are going to learn about three existence theorems: the intermediate value theorem, the mean value theorem, and the extreme value theorem. The question is, which of the theorems are we going to utilize in order to explain why there must be a distance so that the temperature is 63 degrees Celsius? Since we have not discussed the mean value theorem or the extreme value theorem yet, it is not going to be either of those theorems, and we are going to use the intermediate value theorem to explain this justification. Now, in order to use the intermediate value theorem, my function must be continuous. And the reason that this function t of x is continuous is because it is first differentiable. And so I am going to make the connection that because t of x is differentiable on the closed interval from 0 to 12, t of x must also be continuous on the closed interval from 0 to 12. The next thing that we're looking for is to make sure that the table of values indicates that the temperature of the rod must be 63 degrees Celsius at some distance between 0 and 12. And so looking at your table of values, what you'll notice is that on the subinterval from 5 to 7, 66 and 60 are the y values, and so 63 must have been achieved at some point in between x is equal to 5 and x is equal to 7. And so I'm going to indicate through my answer that because t of 5 is equal to 66, t of 7 is equal to 60, and 63 is between 60 and 66. Therefore, there must be a distance between 5 and 7 such that t of c is equal to 63 degrees Celsius.